Okay, so we've been talking about some important examples of vector fields. One of them was an inverse square field. This is sort of my generic inverse square field here. And then in the last video, we were also talking about conservative vector fields. Well, what we're going to see right now is that inverse square fields are conservative. Now, that's not to say that every conservative field is an inverse square field. It's conservative, remember, if it's the gradient field for some real valued function that we call the a potential function, okay? But every inverse square field is the gradient of some potential function. So I could write f as the gradient of some real valued function f, little f. Now, eventually we're going to learn a test for how you can see whether a vector field is conservative, and if it is, then how you can find a potential function. Right now, we don't know that thing. So what I'm going to do is I'm just going to give us the potential function. Now, this statement is true whether we're in 2 space or 3 space. I'm going to just prove it in 2 space. The book actually does it for inverse square fields in 3 space. They just show a little less detail. So I'm going to show more detail, but just do it in 2 space. Okay. So I'm going to say f of xy is going to be the opposite of c. So I'm going to take the opposite of whatever that constant is. So if it's positive, I'll take negative. If it's negative, I'll take the opposite. It'll become positive. Of this over the square root of x squared plus y squared. Notice this is just the magnitude of r. So what I'm going to do is I'm going to take the gradient field of this, and I'm going to show that I get this. Now, that means it's probably going to be a lot easier to see if I write this in terms of its components. So let's just remember that c over the magnitude of r cubed would be the square root of x squared plus y squared cubed, and r was just my position vector x comma y. And I'm going to distribute, well, it's not really distributing, I'm going to do the scalar multiplication, and as I do that, I'm just going to rewrite this as x squared plus y squared to the 3/2 power. So I'm going to get cx over x squared plus y squared to the 3/2, comma, cy over x squared plus y squared to the 3/2. So let's just take the gradient of this and see that we do in fact get that. So the gradient of f is going to have the 2 partials of this function here. I'm going to just rewrite this as negative c times x squared plus y squared to the negative 1/2 power. Okay. And that way when I take the partials, I'm bringing down a negative 1/2. So that's going to give me a positive 1/2 c times x squared plus y squared to the negative 3/2. And then chain rule times the partial with respect to x of the inside part, which would be 2x. Similarly, when I calculate the partial with respect to y, I bring down that negative 1/2, so I get positive 1/2 c, x squared plus y squared to the negative 3/2. Derivative of the inside part with respect to y is going to be 2y. I'm just going to rewrite this a little bit, writing each component as a fraction. So here I've got a 2 in the denominator, a c on top. Negative power here is going to tell me that that's x squared plus y squared to the 3/2 on bottom, times a 2x on top, and I can cancel those 2's. Then same thing here. 1/2 puts a 2 on the bottom, a c on top. That's an x squared plus y squared to the negative 3/2 with a 2y on top, and the 2's cancel. And so I can see that what I'm left with is exactly this. So this is f. So that illustrates that f is actually a conservative vector field, which is kind of nice to know. And if you are asked to prove that an inverse square field is conservative, this is the way to do it. I don't expect you to have memorized that this is a potential function. I would give it to you if I were asking you to prove this again. But you do need to know how to rewrite your inverse square field in terms of the individual components. Okay, one last definition I wanted to give you in this section, and that's flow lines. Now we're not going to spend a lot of time on this. There's one problem in the homework that I didn't assign. It's question number 35. I didn't assign it because it deals with differential equations. And if you're not in differential equations, it's been since 3B since you studied them, and you've probably forgotten. And I didn't think it was worth spending class time to review differential equations just to be able to do this one example. But for those of you who are in differential equations, you might want to check it out if you have time. Okay. But everybody should know the definition of a flow line. Okay. So I've got some vector field up here. I just haven't drawn in the vectors. Here's a curve. This will be a flow line if at every point on this curve, the vector in my vector field is tangent to it. So this is the curves such that at each point, the vector field, I want a better marker. The vector field at that point is tangent to the curve. Now, the name flow line is kind of loaded, so I want to just address the significance of that. If my vector field were a velocity field, so that all of these vectors, some of which are touching the curve and some of which aren't, okay, this curve can't be everywhere at once, okay, if these actually represented the velocity of some fluid that's flowing, then the flow line would actually be the path along which an individual little droplet of water would be flowing. Okay, so that's sort of why they're named that. If my vector field is a velocity field, the flow lines are the paths along which the liquid is flowing. However, if I have a force field, okay, forces do cause objects to move, but forces cause acceleration. So if I have a force field, the directions of these vectors are not necessarily the directions in which the object is moving, they're the directions in which the object is accelerating. We still call them flow lines, but we don't want to think of them as the paths along which anything is moving. With electric fields, electricity is causing electrons to move. They're flowing, kind of slowly, but they're flowing, okay? And they're not traveling along the path of the flow lines. They're accelerating in the direction of these vectors at every point. We call them flow lines regardless. Definition is just that they are the curves so that the vectors in my vector field are tangent to the curve at every point.